Hey folks, welcome to my channel, and in this video we're going to discuss about basics of neural networks and the basics of a perceptron, which is a building block of neural network.
Now let's get started with the basics of neural networks. So what is a neural network? It's a collection of neurons and connections between them. Neural networks is an algorithm inspired by neurons in our brain. It is designed to recognize patterns in complex data and often performs the best when recognizing patterns in audio, images, or video. This is how a typical neuron looks like. A neuron gives out an output, takes in a bunch of inputs, and it performs a function on these inputs. For example, we have a neuron, and let's say I would give three inputs, three numbers 10, 7, and 3. And let's say it performs a function and should give out an output saying 0 or 1. So 1 being true and 0 being false. So what is the function that I'm going to perform? If the weighted sum is greater than 10. So what is this weighted sum? There is a weight that is associated with each input. Let us say this is 0.5, and the weightage given to 7 is 1.0, and the weightage that's given to the third input, that is 3, is 0.1. These are just random values that I'm giving. Now what is the weighted sum? That is 10 times 0.5 plus 7 times 1 plus 3 times 0.1. Now the weighted sum is 12.3, which is greater than 10, so it is true. Now the output that I get is 1. In other words, I would say this neuron is activated. If the output was 0, we would make a statement that the neuron is not activated. This is all that neuron does. Now there is another terminology which is important in our discussion, that is connections. So what is this connection? It is nothing but a channel between the neurons. It connects the output of one neuron to an input of another neuron. Each connection has one parameter that is called as weight. I'm representing weight by theta. Now this is called as weight. So what is this weight? Weight will tell the neuron to respond more to one input and less to another. In the sense, let us say we have inputs from other neurons as well. It comes from other neurons. And the weightage that's given to these are different. Let us say this is 5, the weightage given to another input is 0.1, and the weightage given to another input is 10, probably 0.01 to another input. Now the weightage given to the third input, let us say this is from neuron A, and this is from neuron B, and this is from neuron C. The weightage given to the output of neuron C is more compared to all the other inputs. These weights are adjusted during training, and this is how the neural network learns. Now, how do we structure a neural network? It looks something like this. A bunch of input neurons. This is the input layer, and it can have more than one hidden layer, and that can have any number of neurons. And it also has an output layer, and it can have any number of neurons. Now, each neuron in one layer is connected to all the other neurons in the next layer. So the first one in the first layer is connected to all the 4 neurons in the hidden layer. And the same applies to the second neuron as well. Let us connect the hidden layer neurons to the output layer neurons. Now this is how it's going to look like. Now this takes in 3 inputs. Now, to prevent the network from falling into anarchy, the new neurons are linked by layers. Now, neurons are not connected within the layer, but they are connected to the neurons in the next and the previous layers. And the data goes strictly in one direction, from the inputs to the outputs of the last. If we now throw a sufficient number of layers and introduce more neurons and put weights correctly, because each of this is a channel and there are weights associated with each channel. There are a lot of weights. Now let's take an example. Now we want to build a neural network and train that neural network to recognize handwritten digits. Now, if we throw a sufficient number of layers and put weights correctly, we get the following architecture here. By applying to the input, let's say the image of a handwritten digit 4, black pixels activate the associated neurons, and these neurons activate several neurons in the next layers, and so on. And it keeps on happening until it finally lights up the exit, which is in charge of 4. This result is achieved. When doing a real life programming, nobody is going to write neurons and connections. Instead, everything is represented as matrix calculation, and that is completely based on matrix multiplication for better performance. After we constructed a network, our task is to assign proper weights so neurons will react correctly to incoming signals. Now is the time to remember that we have data, that is samples of inputs, and proper outputs. We have labels and we have predictors. Now we will be showing our network a drawing of the same digit 4 and tell this neural network to adapt its weights. So as I mentioned earlier, each connection is associated with a weight. And we have lots and lots of weights in this neural network. Now we want to make sure that to get the output 4 for this particular image, this is the neuron that needs to be activated. And for this neuron to be activated, we want these 2 neurons to be activated. In the sense, weightage that is given to these 2 neurons should be higher when compared to weightage given to the inputs from the other neurons. And that's how we want to back propagate and adjust all the weights. So we would be showing our network this drawing of 4 and tell it to adapt its weights so that whenever it sees this input, its output should emit 4. To start with, all weights in this network are assigned randomly. Once we show it a digit, it emits a random answer. It need not be necessarily 4. Why? Because the weights are all different. It does not know how much weightage is to be given for different inputs. Then what we do is we traverse back and then we would adjust all the weights. After hundreds and thousands of such cycles of check and calibrate, there is a hope that the weights are corrected and they act as intended. Finally, after such iterations, relevant neurons get activated and the desired response is obtained. The science name for this approach is called backpropagation, or also called a method of backpropagating an error. Why? Because in the initial stage, when it just gives out a random number, maybe it says it is 1 for this particular image, then we would backpropagate this error. This neuron shouldn't have been activated, or the weightage given to these two neurons should have been less, but the weightage given to these two neurons should have been more, something like that. Once we backpropagate this error and calibrate the weightage given to these inputs, finally, after such a number of repeated activity, we will be able to achieve the desired response. Now let us get into the mathematics of neural networks. I'm going to now draw a perceptron, which we discussed earlier, and I'm going to provide a few inputs. You can have any number of inputs. And then we are going to take weighted sum of these inputs. Let us say this is input x1, x2, and this is xn, or let's say m. And there are weightage given to each input. So Wm, we have as many weights as the inputs, and we are going to take a weighted sum. Also, we would compare it with a threshold, and then based on that we would get a binary signal. This is how it's going to work. Now, mathematically, how do we express this? Now, a threshold is given by a function, and we pass a weighted sum to this function, and based on that we would get either 0 or 1 if z is less than or equal to some threshold value, or it will be 1 if z is greater than some threshold value. Now, this could also be written as function of the weighted sum, which is summation of inputs multiplied by corresponding weights. I takes values from 1 to m, which is parameterized by the threshold value theta. Simple. Now this could also be written as y cap. Now, how are the inputs written? We express these inputs in the form of a vector. So, we have x0, x1 until xm. You might wonder what is x0. x0 is the bias term. This is called bias unit. And also we have weights, which starts from W0, W1, W2 until Wm. So where does this bias come into picture? Bias is one more input to this neuron. This would be the bias unit. And there is no weight associated with it. Now where do we add the bias term? Bias term usually gets added to the weighted sum. Now the common notation is to define the bias unit separately. However, it's inconvenient for mathematical notation. So that is why we would define bias unit as W0. And what we do is we prepend 1 to each input vector, so that when you multiply x with w, you would multiply 1 with W0. 1 times W0. And that's how you would get B. It is easier to express in terms of matrices instead of defining it separately. Modifying input vectors is more inconvenient, or it is inefficient coding wise. So that is why what we will do here is we would associate a weight here instead of the bias. This would always be constant 1, but it would have a weightage W0. We are expressing the bias term in the same way we are expressing weighted inputs. Now let's talk about how perceptron works. Let's imagine we have a classification problem and we have some bunch of data. Now assume a binary classification task. Now a perceptron finds a decision boundary if these classes are separable. What it does is it would find a boundary. In machine learning, perceptron is nothing but an algorithm for supervised learning of binary classifiers. In machine learning, the perceptron is an algorithm for supervised learning of binary classifiers. So what is a binary classifier? That is a function which can decide whether or not an input represented by some vector of numbers belongs to some specific class, whether it belongs to the group red or group blue. It is a type of linear classifier, that is a classification algorithm that makes its predictions based on a linear predictor function, combining a set of weights with the feature vector. Now let us start with the basic terminologies. As always, let's draw a basic network which has 2 input nodes and a hidden layer consisting of 3 nodes and an output. Now all of these are connected. Each neuron in the first is connected to all the neurons in the second, and all the neurons from the second layer is connected to the last layer, and this is how the inputs flow. It's always unidirectional. Now we call these neurons for activations A at layer L, and this is given by a function. Now activation function is given by g of z, which is at the layer L. Now, what exactly is z term? This is nothing but a weighted sum. Z at layer L will be equal to weights multiplied by activations from the previous layer, L minus 1, in addition to the bias term. Now the nodes are connected in some way. Each neuron holds a number, and each connection holds a weight. These neurons are split between input, hidden, and output. Now the idea is that we input data into the input layer, which sends numbers from our data ping-ponging forward through different connections from one neuron to another in the network. Once we reach the output layer, we hopefully have the number that we wished for. The input data is just your data set where each observation is run through sequentially. Now each neuron has some sort of an activation, and this value ranges from 0 to 1. Now 1 is the maximum activation and 0 is the minimum activation that a neuron can have. That is, if we use the activation function called as sigmoid function, which looks something like this. Now we have an activation function which is used commonly. This is called a sigmoid function. It just scales the output to be between 0 to 1. So it is a logistic function. This is given by g of z that we have wrote earlier, and 1 over 1 plus e to the power minus z. So by plugging in z value, you would either get you would get some number between 0 and 1. Now we wrap the equation for new neurons with activation, that is, multiply summarization of a result of multiplying the weights and activations. Now what is the significance of this bias term? Bias is trying to approximate where the value of the new neuron starts to be meaningful. So you would try to add or subtract the bias from the multiplication of activation and weights. This is modeled as a vector multiplication. Now we find that the neurons and the layers are formatted in linear algebra. Let's try to expand the above expression. Now we have a sigma, that is the activation function. We would pass z, that is the weighted sum. So let's write the weighted sum. And so on until we have n number of neurons. In the previous layer, of course, and we would add or subtract the bias term, and this will be the new neuron. Now these are the activations of neurons in previous layer. This is something to remember, and this would be the bias term. So the general notation is A, and which is the neuron, the index of that neuron, and the layer in which it is present. For example, let's say we want to write the activation of third neuron in second layer. Since index starts at 0, third neuron is represented by A2, and the second layer is represented with superscript 1. Generally, weights are denoted by to and then from. Why is it so? Either we represent with W or theta, both are fine. Because when we represent these in terms of matrices, this order makes sense. Now let us say to third neuron in the third layer from fourth neuron in the second layer. In the sense, we want to write the third neuron in the third layer from fourth neuron in the second layer. That will be W2, 3, and the layer will be 2. This would be the third layer, and this would be the third neuron, and this would be the fourth neuron. From fourth neuron to third neuron. This is the weightage given to the input from fourth neuron to third neuron. Now let's try to understand how we could represent neural network in terms of matrix multiplications. Now let's consider two layers consisting of several neurons. Now layer 1 can have k number of neurons, and layer 2 could have j number of neurons. Now the output of one neuron, as we know, is connected to the input of another neuron, and it is associated with weight W. Now let's write a simple expression. Now this would be the activation of layer 2. And this would be the activation from layer 1. This is a vector. It is not a single value, but it is a vector. And this as well is a vector. A vector which is consisting of activations of all the neurons in this layer. Now, if we try to expand this, this is how it's going to look like. This is the matrix W, which consists of all the weights from neurons in layer 1 to neurons in layer 2. This would be the vector A0, that is all the activations from layer 1. As you can see that weighted sum is represented by matrix dot product, and we are adding bias to the weighted sum. So what we do here is we take all the activations from the first layer, and then we do a matrix multiplication with all the weights connecting to each neuron from the first layer to the second layer. And finally, we wrap the entire thing with a sigmoid function, and we apply this function on the resultant matrix. From this we get a matrix of all the activations in the second layer. To summarize, in neural net visuals, circles represent neurons and the lines represent the synapses or the connections, in other words, a channel. Now these synapses have a really simple job. They take a value from their input multiplied by some weight, theta or w, and then they output the result, which will become an input to another neuron. Now neurons are a little more complicated. Their job is to add together the outputs of all their synapses and then apply an activation function, that is sigma of z. Certain activation functions allow neural nets to model complex nonlinear patterns that simpler models may miss. For our neural net, we will use sigmoid activation function, which looks something like this, ranging from 0 to 1. In the next video, I'm going to talk about forward propagation, and we will be going in depth into all the mathematics behind it. It's going to be very interesting. Do check out.